Welcome back. This is video lecture 29.3, and we're talking about section 3 in chapter 29, and we're going to introduce a new method for calculating magnetic field. It is historically known as Ampere's law, and yes, that's the ampere of the unit of current. Bigger picture, Ampere's law in magnetostatics, chapter 29, plays the same general role as Gauss's law in electrostatics, chapter 23. Okay, so you could, loosely speaking, say Ampere's law is the magnetic version of Gauss's law, in that it plays the same role as Gauss's law. So let's have a little reminder of Gauss's law. That might be useful. Gauss's law in words says, the integral of electric field over a closed surface, and we have a name for that quantity that you get when you integrate electric field over a closed surface, like the surface of a blown up, stretched, and tied off balloon. And that name for the integral of electric field over a closed surface is electric flux. Remember that name? All right. The integral of electric field over a closed surface, electric flux, is proportional to the total electric charge inside the surface. That's it in words. Here it is written down in much more concise mathematical notation. We're doing the integral over a closed surface of electric flux. So E arrow dot dA arrow. That's the left side. That's called electric flux through a closed mathematical surface. And the answer will be proportional to the total electric charge, that's supposed to be ENC for enclosed, divided by one of our old friends, the constant in electrostatics, epsilon zero. And then there's a picture here just to bring back some ideas of two charges, positive and negative. Turns out they have equal amounts of charge, and several different surfaces, mathematical closed surfaces of different shapes. There are 4 of those surfaces, in fact. And you're seeing them in cross-section. Surface S1 has this volume inside it, right here. And you can see it's got electric field lines piercing going outward, just by looking at the diagram. So there's a positive electric flux through surface S1. And when you go about the integral of E dot dA for surface S1, that would be pretty complicated to do, that integral of E dot dA, because the surface S1 is pretty complicated shape. But you don't need to go through all that, because the answer for the integral of E dot dA will just be the total charge inside over epsilon zero. And there's only that one positive charge right there. So all you need to know is how big that charge is, and then divide by epsilon zero. Now let's look at another surface, the one down here, which has this volume inside it, S2, it's labeled. Okay? Well, we can see that that has electric field lines piercing going inward for S2. So I know there's negative electric flux through S2. And I could try to do the integral of E dot dA to get that flux, but it'd be pretty complicated because S2 is a complicated shape. But I don't need to do that, because I know the answer for the integral of E dot dA will be equal to Q enclosed over epsilon zero. So all I have to know is what that charge is. And it'll be negative, so I'll have a negative Q over epsilon zero, and that'll be the electric flux. Now let's pick a different surface. Over here is S3, and there's the volume inside it. Another pretty complicated shape. But I have a good sense of what the electric flux is going to be through that one, because every electric field line that pierces S3 going inward, like right there, also pierces coming outward. There. Or this one, piercing coming in, and then piercing going out. Piercing coming in, and then piercing going out. Sure looks like the electric flux through S3 is equal to 0. But Gauss's law says I don't have to actually do the integral of E dot dA to get the electric flux. I can just take the total Q enclosed and divide by epsilon 0. Aha! But there is no Q inside S3, yes? None at all. So the Q enclosed is 0. So the integral of E dot dA for surface 3, that's 0. for that surface. And then there's surface 4. See it there? It's surrounding pretty much everything. It's this whole volume here inside it. Okay, and if I want the electric flux through that, well, I can try the brute force integrating E dot dA, but I'm already looking like I see what I'm going to get. Because for every electric field line that pierces S4 coming outward, like right there, there's another one that pierces coming inward, like right there. And so it looks again like I'm going to get an electric flux equal to 0. Gauss's law tells me exactly how to know for sure what the electric flux is. I just need the total Q enclosed. Total Q enclosed. Well, I have two charges inside S4, the positive one and the negative one. And if those charges are equal, which they are, then the Q enclosed is 0. Okay, hold on here, folks. Okay, we're still going okay. Thought I had a technical glitch, but I think we're okay. All right, so now, let's go on and start practicing with Ampere's law. Let me bring that down so you can see it a little bit better. I'm going to state it. I'm going to state it, and we're going to start practicing with it. And it's going to have somewhat of a similar sound when we say it in words to Gauss's law, but it does have some subtle differences with Gauss's law, and we have to be very aware of those. All right, here comes first the statement of Ampere's law in words. Another integral, just like in Gauss's law, but now we're going to integrate magnetic field, B arrow, and we're going to integrate it around what is called a closed loop. Careful, not a closed surface. There's an important distinction, okay? Loop. So here's what I want you to envision. When I talked about a closed surface with Gauss's law in the electric field case, I said imagine something like a blown-up balloon that's been filled with air and tied off. And then the surface of that balloon is a closed surface. Here we have a closed loop. All I want you to imagine here is take a length of string, cut it, and tie the two ends together. And you have a closed loop. Now we're going to have a mathematical version of that, which means it may not necessarily be something you can actually touch like a piece of string. It might be a purely mental, mathematical construct. But that's a way to envision a closed loop. What you would get if you take a certain length of string and tie the two ends together. Then, say, a little ant could walk around the string and never fall off. It would just keep going around and around and around. That's a closed mathematical loop. Okay? And now what we're doing with Ampere's law is we're going to integrate magnetic field along or around a closed loop. And by the way, we'll give that a name, that quantity. We had a name for what we call when we integrate electric field over a closed surface. We called it electric flux. So we're going to give a name to the integral of magnetic field around a closed loop. We're going to call it magnetic circulation. All right. So the integral of magnetic field along a closed loop is proportional to the total electric current piercing the interior of the loop, the interior area of the loop. It helps if we draw some pictures, okay, and have something specific in mind. So let's look at this next picture. Here you're seeing three very long, straight, parallel wires, looking at them from the end, okay? And wire 1 carries current I1 out of the screen towards you. Wire 2 carries current I2 into the screen away from you. Wire 3 carries current I3 out of the screen towards you. There's wire 1, there's wire 2, there's wire 3. And somebody has chosen, like the piece of string with the two ends tied together, a closed loop for doing an integral around. And it's this curve drawn in red. And it's called, when you're using Ampere's law, an Amperian loop. Just like we called the closed mathematical surface in Gauss's law, Gaussian surfaces. Now we have Ampérian loops. Somebody has chosen that, okay? And given it to us. It looks kind of like a kidney bean shape. All right. And we are interested in what's called the magnetic circulation around that loop. And that means take the total magnetic field at any given point on the loop, and in fact the picture draws that in one place, okay? Right here. This arrow represents the net magnetic field, B, at that location right there on the Ampérian loop. And that's the total B, net B, from all sources of magnetic field in the picture, which in this case are those three currents or wires. And at that one point on the loop, it points in the direction there. And we break up this loop into a whole bunch of little tiny displacements, ds. There's the one for where we are. It's tangent to the loop, see the dashed line? And in a direction that we choose. Oh, it's listed here as direction of integration. We choose that. We chose the ds to be basically as close as you can get to the direction of B. All right, and now we're going to calculate B dot ds, and I mean B arrow dot ds arrow, actual dot product of two vectors, which means take the magnitude of the first vector, magnitude of the second vector, cosine of the angle between them when they're drawn with a common tail. I'll call that angle theta. You can see it's actually labeled in the diagram. And you'll get some scalar number when you do that for that one little piece. Then you have to go on to the next little piece of the wire, the next little ds, or the loop I should say. Right there. You got to find the net B right there. That might be directed that way. You've got to do B dot ds for that little piece of the loop. Then you got to go on to the next little piece, ds, tangent to the loop. You got to find the net B there. That might be that way. You got to do B dot ds for that. And you just got to work your way all the way around the loop once. And you got to add up all the B dot ds values. And the total will be called the magnetic circulation. And that would be denoted with that symbol. B dot ds, integral symbol with a little closed circle on it, which is a reminder that it's closed, in this case a closed loop. Okay, now what Ampere's law does is tell you what you're going to get for the answer for that integral. Just like Gauss's law told you what you're going to get for the answer for the integral of E dot dA over a closed surface. Ampere's law tells you what you're going to get for the answer for B dot ds around a closed loop. And the answer is proportional to the total current enclosed, or if you like, encircled, even though the loop may not be an actual circle, by the loop, surrounded by. And so here for the I enclosed, what you've got to do, let me declutter my diagram a little bit, is you've got to imagine the area inside the Ampérian loop that has been chosen, okay, like it's almost like it's like a kind of a membrane. And you've got to account for all of the current that pierces that membrane going through it, okay? Because that's what goes on the right side here, I enclosed or encircled. You can see from in our particular drawing that the current in wire 1 does pierce that interior surface, and the current in wire 2 does as well. But the current in wire 3 does not pierce the interior surface. And so I3 would not be included in this I enclosed. Does that make sense? You've got to be able to identify whether a current pierces the interior surface of the loop or not. But there's a little more to it than just that. Okay? So we're figuring out now what to put for I enclosed for this loop. So now in the second picture, same loop, okay? But they've only drawn now I1 and I2, reminding you which way those currents are going. A little bit slightly different perspective here. I1 is up, I2 is down. And the way you account for the I enclosed is this. It's another variation on a right-hand rule. Sorry, but right-hand rules are everywhere in magnetism. It's just the way magnetic fields behave. Here what you do, the I enclosed right-hand rule, you might call it, is you imagine reaching in with the fingers of your right hand and putting them as if you were going to hold on to the loop with your fingers in the direction the current's going around the loop. Sorry, I said that wrong. I beg your pardon. With your fingers in the direction that we integrated to get the circulation. Remember that up there? That's what the way your fingers go. In the direction of the way we did the integration. And then hold out your thumb like you're hitchhiking. And if your thumb points up. Since we in essence chose the direction of integration here, as you can see, counterclockwise. So I curl my fingers counterclockwise and my thumb points up. That means a current that pierces this interior surface upward makes a positive contribution to I enclosed. That's why it's labeled here plus I1, because that current's upward. Whereas a current that pierces that interior surface going downward makes a negative contribution to I enclosed. And so you'll see they've got it written here as negative I2. So for this particular little situation we're looking at, the I enclosed is I1 minus I2. Okay? All right. Then Ampere's law says that the so-called magnetic circulation integral, the integral of B dot ds around a closed loop, is proportional to this current piercing that we called I enclosed, and we just need the proportionality constant. And it is the new magnetic constant we've been using, mu 0. And that's the mathematical statement of Ampere's law. And I want to just demonstrate a little more to you what that means conceptually with the Wiley Plus animation. So let me go to that. Okay, hold on just a second. Okay, so here is the animation on Wiley Plus that I want to show you. And it might look like there's a lot going on here, but there really isn't that much. There's one wire, the current I. The wire is along the z-axis. The current I in it is going upward in the plus z direction. And there are two closed loops. They're actually simply circles. Path 1 is a circle in the xy plane with its center at the origin. Path 2 is a circle in the xy plane with its center displaced along y a distance big D, which in this case happens to be 3.5 meters. When I run the animation, the picture is basically going to do a graphical version of the magnetic circulation, the integral of B dot ds around the loop. And the way it's going to do it graphically, it's going to take the component of B along the loop, component of B along the ds. So if I look at path 1 at that one location there, the red arrow is the ds at that one point, and the B is in the same direction. Because we know already that the magnetic field produced by a long straight wire circulates around the center of that wire. Look at path 2. Here's the same corresponding ds tangent to the wire, but there's the actual B at that location. All right, so at any given location for each path, it's going to plot what the graph calls B cosine theta, which is just the component of B along ds. And it's going to plot that as you go around once. And basically the area under that curve is the integral. That's the circulation. So I want to see what we get for the circulation for path 1 and path 2 when I run the animation. So it encircles the path exactly once. The purple line is B cosine theta for path 1. Notice it's constant. Notice the area under that purple line is a nice constant positive value. That's the circulation for path number 1. The curve in black is b cosine theta for path 2. And for some parts of the perimeter around 2, b cosine theta is positive, and for other parts it's negative. And the light gray shaded area is the area under the curve, and it turns out that you have just as much positive area as negative area, and it says the area under the curve for path 2 is 0. Okay? And of course, the way you get negative b cosine theta is any region of the curve. I can even backtrack to get to there. It's like right about there, where the b and the ds have an angle between them greater than 90. See the way that is for path 2? That's why you're getting a negative value for b cosine theta. Notice you never get that for path 1. All right, so the magnetic circulation for path 1, not 0. Notice that there is an eye enclosed piercing the interior of path 1. It's that wire, right? It goes right through the middle of that circle. But for path 2, there is no current piercing the interior area, right? The wire is over there at the origin. Path 2 is over here on the y-axis. No current pierces through the interior of wire 2. Of path 2. So now I'm going to reset the animation, and I'm going to make the d a little bit smaller. Let's go down to something like 2.5 meters. Okay? Now, see path 2 got a little bit closer to the wire? But notice that the wire still does not pierce through the interior of path 2, like it does in path 1, yes? So when we run the animation and we get that graphs from which we can get the circulations, what do you think we're going to get for path 2? Think about that a minute. You ready? Make a prediction. Now let's run the animation. Circulating around each path. Look at the graph. Again, I've got a positive area under graph number 1. So I'll have a positive circulation, which means there better be current piercing the inside of path 1. But look how much area under the curve for path 2. 0. So there better not be any current piercing the interior, or any net current piercing the interior of path 2. And there isn't. All right, now let's reduce the d to 1.5 meters. Okay, now look carefully at where path 2 is. You see that the wire now pierces the inside of path 2? And of course, it still pierces the inside of path 1. So what do you think we're going to get for the circulation now? Well, in fact, it tells us, doesn't it? It should have not have told us that. We get a positive area under the curve, don't we? Both for path 1 and path 2. Because both path 1 and path 2 have current piercing the inside, in this case going upward. I can even just decrease the d. I can go all the way down to 0, where then the two paths completely coincide. Then the graphs are identical. Or I can make the d bigger, and as long as path 2 encircles the wire, we get the positive area under the curve, the positive circulation. Same value, right? But if I then let the path 2, get far enough out that it doesn't encircle the wire anymore, then the total area under that curve for path 2 is 0. Let's go back to a case like that, where we are encircling the wire with path 2. Note the area under the curve. Let's use that number to figure out what that current in the wire is. Okay, let me go back to my OneNote, and I'll just come down here to the side. And I'm talking now about the application from the animation. Okay, what we know for path 2, it's also true for path 1, is that the integral of b dot ds is 1.26 microtesla times meter. Note the units for circulation. They must be the unit of magnetic field times the unit of distance or length. So Tesla times meter, it just turned out to be convenient to express it as microtesla times meter. Now, according to Ampere's law, that magnetic circulation must equal mu zero times the current that's enclosed or encircled by the path. And that's just the current in the wire in this case, right? I. So I'm going to set this equal to this and solve for I. Okay? I equals 1.26 microtesla times meter over mu zero, right? That's what it is, over mu zero. That has a well-known value. We need to start getting used to it. 4 times pi times 10 to the minus 7, and the unit are Tesla times meter per ampere. Note that the unit of meter cancel, and microtesla and the Tesla in essence cancel once you account for the factors of 10. You put that carefully into your calculator and check it. You'll see that that current comes out to be 1 ampere. Okay, so if you have a closed mathematical loop and you want to apply Ampere's law to it, Ampere's law tells you that when you integrate B dot ds around the loop once, the magnetic circulation, the number that you get will be equal to just a constant, happens to be mu zero, times the total current that is encircled or enclosed by the loop. And now we'll reuse that, whereas a really powerful idea is to find the magnetic field when you have a lot of symmetry in the current distribution so that you can beforehand guess the direction of B. Because then you can choose an Amperian loop carefully that will make it easy to solve for B. That there has to be enough symmetry in the current distribution that just from that symmetry you can deduce the direction of B. And that's the same approach basically we used with Gauss's law to find E. So let's show you an application. Let's find the magnetic field outside, magnetic field outside a long straight wire. You're seeing it edge on. It's carrying a total current I. It's coming out of the screen in a wire, in a long straight wire. And it's not a thin wire. We often have done wires, but we've treated them as being pretty thin. Let's say it's a hefty, thick wire. Okay. And the current I is distributed through a cross-section like that I just shaded in, and it's done so uniformly. Okay? All right, so I is distributed uniformly over this cross-section. Okay? And the question is, what is the magnetic field produced at an outside point? Like right there. Okay? That's some distance r from the center. Okay, so that's the geometry. And we already know from the brute force method, sometimes called the Biot-Savart law method for calculating B, that if a very long straight wire, the magnetic field line just circulates around the wire. And if I use a special right-hand rule, hold my thumb in the direction of the current and see which way my fingers circulate, that's the way B circulates. So if I hold my thumb towards me on my right hand, because the current's coming out of the screen towards me, I see my fingers circulate counterclockwise. So I choose an Amperian loop centered on the center of the wire that is exactly a circle, and I'm going to do my B dot ds integration counterclockwise. Okay? There's the Amperian loop. A circle, radius r, and we're going to integrate B counterclockwise. And we're going to get an expression for the magnetic circulation around that Amperian loop. The picture shows one particular location on the loop. That represents the net B, the net magnetic field, at that location. Notice it's tangent to the loop. And there's the little displacement or step, ds, tangent to the loop, and we have decided to integrate counterclockwise to go with B. Okay? Notice then the theta, the angle between the B and the ds for that little piece, is 0. And that's going to be true all around this loop. I could draw the B at other places, like right there. There's the B. And the ds would be in the same direction, tangent. And that's true everywhere on the loop. The B and the ds are tangent counterclockwise. So when I do the integral of B dot ds around the closed loop, that means magnitude of B, magnitude of ds, cosine of 0 degrees. And of course 0 degrees is plus 1. So that's just the integral around the closed loop of magnitude B times magnitude ds. Get that down a little bit so you can see it. Okay? All right. Now, the next step is very important. If we cannot do this next step legitimately, Ampere's law is not helpful. I need to be able to bring B magnitude out front of the integral. So that I'm just left with the integral around the closed loop of all the little step sizes ds. Why can I do that? You see why? Why is it legitimate to bring the B out front? You can't just willy-nilly do it. You got to be able to justify it. What's the justification? Do you have an answer? You need to. The reason, which you probably said, is that at every point on the loop, the point we are is the distance r from the center, and the B only depends on how far you are from the center. So every point on the loop is the same distance from the center. Every point on the loop has the same B magnitude. That's why we chose the Amperian loop to be a circle, concentric with the wire. That was the whole purpose of choosing the Amperian loop that way, so that we could bring the B magnitude out front. If you can't find an Amperian loop for which it is allowable to bring the B out front, forget about Ampere's law. It's not going to be helpful. But we can here. And then the integral part that's left is very easy. It says just add up all the little step lengths once around. Lengths. Well, that's just going to be the total length once around, yes? That's called circumference when you're talking about a circle. There's a well-known formula for that. So my expression for the circulation is B magnitude, and the circumference of the circle is 2 pi r. I'm going to number that equation 1. That's the circulation formula for this circular Amperian loop. Now the other thing I need to keep track of, if I'm using Ampere's law, is what is I enclosed? What is the total current piercing through the interior of the loop, the Amperian loop? Let me declutter my drawing a little bit. And now let me highlight the surface that is interior to the Amperian loop. It is this entire surface here that's kind of a disc shape inside the radius r. I need the total current that pierces through that surface that I shaded in yellow. Got to be able to visualize that. And I have to account for whether it's positive or negative. I do this special I enclosed right-hand rule where I circulate my fingers the way I did the B integration, and I see which way my thumb points. We did the B integration counterclockwise, so I circulate my fingers counterclockwise, my thumb points up. So any current that pierces that shaded surface upward is positive. Well, the entire wire inside the current is piercing going upward, yes? The entire wire, the entire current of the wire, I. So the answer for I enclosed in this context is a simple, straightforward plus I. And I'll number that equation too. And now I will actually write down Ampere's law. I haven't really used it yet. Ampere's law says the integral of B dot ds around a closed loop equals mu 0 times I enclosed. So I use equation 1 on the left for the circulation, magnitude B times 2 pi r, and I use equation 2 on the right for I enclosed, total I inside the wire, and I solve for B magnitude. And I get the nice simple result in this case that B magnitude is mu 0 I over 2 pi r. That is outside the wire. Now we found that for a thin wire that was very long and straight, but we had to use the brute force method, and we had to integrate from negative infinity to infinity. Well, we got that answer. We didn't have to do that complicated of a math here, did we? So the magnetic field outside this wire, and it's not necessarily a thin wire, is mu 0 I over 2 pi r. Now let's do something else that we would not have been able to do easily with the brute force method. Same long straight wire that's thick, with the current I distributed uniformly over its cross-section. And now let's find the magnetic field at a point in the body of the wire, like right there. Wow. Yes, you can have a magnetic field in there. Okay? And we're going to apply Ampere's law to that, to find that B. We still have this tangential symmetry, because the current's still coming out of the screen towards us. The magnetic field has to be circulating around the center of the wire counterclockwise. So at that point that I marked, the B is tangent to the circle counterclockwise. So that'll be the direction we'll integrate. All our little DS's, like this one, is tangent to the Amperian loop, counterclockwise. So it's that same kind of symmetry. I can just immediately write down, symbolically, that the circulation formula for this circular Amperian loop is B magnitude times 2 pi r. Right? So we can still call that equation 1. That's fine. But now I have to ask the next question, what is I enclosed? So now let's be clear. See where the Amperian loop is? It's got a radius little r. Okay? Whereas the whole wire itself, note by the way carefully, we've denoted its radius with a big R. So our Amperian loop's radius is little r. That's drawn in kind of orange there. The wire's radius is big R. So where's the surface interior to the Amperian loop? It's only that disk of radius little r. Right? I'm trying to shade that in like that. It's that surface that I have to get the I enclosed for. No other surface. That. Now, how do I get that? Well, we'll just do it by kind of ratio reasoning. Remember that the I over the whole cross-section, radius big R, the current, is the I. How much of that current is through the radius little r? Well, like I say, we'll do it in ratios. The ratio of the I enclosed that we have over the total I is equal to the ratio of the area we have in our Amperian loop, pi little r squared, to the cross-sectional area of the whole wire, pi big R squared. That makes sense? Pi's, of course, cancel, and I just multiply both sides by the total I of the wire, and I get that expression, which I'm going to now label equation 2. The enclosed current is the total current times the ratio of little r to over big R squared. And that works for any little r between 0 and big R. Any little r between 0 and big R. Notice when little r equals 0, I enclosed equals 0. When little r equals big R, I enclosed equals I total. And then we just put these two expressions together in Ampere's law. And we'll be solving then for the B magnitude at a point inside this long straight wire. Okay, I use equation 1 on the left, B magnitude times circumference, 2 pi r. And I use equation 2 on the right. Mu 0 I times little r squared over big R squared. And I solve for b. I can divide both sides by 1 factor of little r, and I get b magnitude equals mu 0 I little r over 2 pi big R squared. And this is valid anywhere inside the wire. And notice the variable, which is little r, is upstairs. Everything else is a constant. So in the interior part, notice if little r is 0, b is 0. The magnetic field grows as you go farther away from the center. In fact, let me come over here to the side, over here, and let me just sketch the magnitude of the magnetic field as a function of radial distance from the center. That's now what the little r means, radial distance from the center of the wire. One important point on that axis then is big R, when you hit the radius of the wire. And so that means any little r value, of course this is 0 for little r, any little r value between 0 and big R means you're at a point inside the wire, and any little r value larger than big R means you're at a point outside. And now I just plot this using the inside wire part for R less than big R, and the outside wire part, mind you, right there, which has an R downstairs if you're outside the wire. So inside, the wire grows linearly with R. So you just have a line going up like so. The slope of it is mu 0 I over 2 pi big R squared. Sorry, I didn't go past that point. All right. And then over here, that's the b value when you are at the surface. When I put in little r equal to big R, I get mu 0 I over 2 pi big R. Sorry, make sure you can see that. Okay? And then you're at little r equal to big R. You're right at the surface of the wire. And then you go outside and you need the 1 over R result. And it just goes down, getting smaller and smaller. And notice the field is continuous. It just picks up where the inside result leaves off and gets smaller. Okay, that's our first application of Ampere's law. We found the magnetic field at all points inside and outside, a long, straight, thick wire. And we'll be doing more applications of Ampere's law in class, so I will just leave you here with a class engagement exercise to practice with Ampere's law. Okay? All right. The figure here shows 3 equal currents, I. 2 of them are parallel and 1 is anti-parallel. In other words, 2 of them are up in the plane of the screen, the other one is down. It also shows 4 Amperian loops, A, B, C, and D. Now we have to be clear about how these loops work. And they're trying to show you in the diagram, if you look very carefully, how these loops are positioned relative to the wires. For example, loop A, I have a solid continuous black curve around the front, so it's in front of us, going around. And if you look very carefully, there's a gap at the back. That's trying to convey to you that that loop is going behind that wire. And then there's another gap, so the loop's going behind that wire. And then there's another gap, and the loop's going behind that wire. And that's loop A. Now in loop B, let's start roughly here. It's continuous, so this part is in front of the wire. But then there's a gap. So that's behind the wire. Then it's continuous, so that part's in front. Then there's a gap, so it's behind. Then there's a gap, so it's behind. Then there's a gap, so it's behind. You have to be able to tell from the figure whether the wire pierces the interior of the Amperian loop or not. Here's loop C, nice little circle. Continuous in the front, so it's in front of the wire. And there's a gap there so that it's behind the wire at the back. And here's loop D. Continuous in the front, so it's in front of the wires, and then gap, so behind, gap, behind. Those are the 4 Amperian loops, all right? 3 wires, 4 Amperian loops. The loops are labeled A, B, C, and D. Here's our task. Rank the loops according to the magnitude of B dot ds, the magnetic circulation along them. Greatest first. Assume each loop is integrated counterclockwise when viewed from above. So that'd be like this, for example. And that'd be like this, and like this, and like that. All right, so you want to rank what you get for the magnetic circulation, integral of B dot ds, around these loops, biggest to smallest. Okay, that's our task, and we'll be practicing with Ampere's law in class. And that's all for this video.